Hello everyone, my name is Khalid Tahboub and I'll be talking to you today about PCA, Principal Component Analysis, and why isn't it good for dimensionality reduction. This is a student lecture, part of the ECE 662 class, which is the Pattern Recognition and Decision Making process. If you are interested in watching more lectures, please visit www.projectria.org. Those lectures are available in multiple languages. This is the outline for my talk today. I'll start with a brief introduction about PCA, what it's used for, and then I'll review some of the prerequisite material, such as eigenvalues, eigenvectors, variance, and the covariance matrix. Then, with some examples, I'll explain the steps involved in PCA. Please keep in mind that this lecture is not supposed to give you a solid theoretical background, but more an intuitive understanding, and why PCA is not always good for dimensionality reduction. I'll end up with some reasons that might cause PCA not to be the most efficient solution for dimensionality reduction. So what is PCA? Principal component analysis is a statistical procedure based on orthogonal transformation. As we will see in the next slides with some examples, how we transfer the data we have using this kind of orthogonal transformation. It has different names. Sometimes it's called the KLT, or the Hodling transform, proper orthogonal decomposition, singular value decomposition, SVD, eigenvalue decomposition, factor analysis, and many other names. And this is because PCA is used in many different fields. It has been introduced in different fields with different names, and its widespread causes this kind of different names. So again, it's a statistical procedure and transforms the data we have to a linearly uncorrelated new coordinate system. This coordinate system might have the same dimensionality as the original data or a lower dimensionality. And each component in this new system is called, might be called principal component. So let's assume we have data, so we have samples from our data that we're interested in. We want to analyze the data and classify the data. In some cases we have higher dimensionality, and it's not easy to deal with higher dimensional data. So we want to reduce the dimensionality, and we use, sometimes PCA is used for that purpose. So we try to find the principal components and transform our data into those principal components at the same number of dimensions or a lower number. And in practice it's used for compression, because once we decrease the number of dimensions, we're getting rid of some information and we're actually compressing the data we have. Other things involve pattern analysis. As we'll see, by this kind of reduction, you're actually looking into the patterns involved in the data. So let's start with eigenvalues and eigenvectors. Eigen is a German word that means unique, and basically the idea is that if we have a matrix A and a vector B, and we multiply the matrix A by vector B, we get a scaled version of the same vector B. So if you look over here, we have the matrix A and we have the vector B, and the multiplication is equal to the vector itself, scaled version. So the matrix multiplication is just equal to, or let's say equivalent to, a constant multiplication. And this is what is unique about this process. When we have such a case, we call vector B an eigenvector, and we call this constant an eigenvalue. Keep in mind that you can actually scale, if let's say, if the vector 1, 2, 3, imagine that we're talking about 3 dimensions, and we have the vector 1, 2, 3 is an eigenvector. 2, 4, 6, just multiply the same vector by 2, is also an eigenvector, because we can scale both sides and we'll end up with the same equality. So vector B is the eigenvector for matrix A, and the constant is the eigenvalue for this specific eigenvector. This is one example. We have the matrix A over here. We have the eigenvector 1, 2, 3, 1, 2, 3. We see that if we multiply this vector by 14, the same thing exactly as we multiply this matrix. So in this case, we say that 1, 2, 3 is one eigenvector for this matrix, and we say that 14 is also the eigenvalue for this specific eigenvector. To have for a 3 by 3 matrix, we can have up to 3 eigenvectors, and for each we have an eigenvalue. To read more about eigenvalues and eigenvectors, you can refer to one of the textbooks involved in linear algebra. Variance and the covariance matrix. Variance is a measure of the spread of the data. So let's say you have samples in one dimension. You want to see how much we have spread around the mean of the data. We introduce the concept of the variance, and this equation gives us the variance value. And as you can see, we take all the values from all the samples. Let's say we have n samples, so we start by x1 up to xn, and what we do is subtract from the mean value, square the value, and then the summation of all these operations over n minus 1. The covariance is a measure of how much two dimensions vary from the mean with respect to each other. So assume you have two coordinates. You want to see how they vary from the mean with respect to each other. In this case, we change the equation of the variance in this form. We have xi minus x bar and yi minus y bar. So for x and y, we have n samples, of course, and this gives us an indication how they vary with respect to each other. Okay, the covariance matrix is another representation. So assume we have these samples for x, and each sample has n dimensions. As explained in the previous slide, we find the value of the covariance in a way that involves two of the dimensions. What about if we have a value of number of dimensions higher than 2? In this case, we introduce the idea of the covariant matrix, in which we analyze the covariance of each two components of the n dimensions at a specific point. So the covariant matrix is an n by n, so n is the number of dimensions, and the covariant matrix has n by n elements, and each element is basically the covariance of the corresponding element. So let's say ij in the matrix is equal to the covariance between xi and xj, assuming that we have x1 up to xn, and it's the same equation for the covariance we saw before. So this is how we find the value of the matrix. Now let's look at an example. We're going to reuse this example in the future to understand the PCA process. We have data that has two dimensions, and we plot the points. We see this kind of relationship. If we look at each dimension alone, we can find the value of variance for each one of those. So variance of x1 is 12.0114, and values of x2 is 43.5705. Now we want to understand how they vary from the mean with respect to each other. So we use the covariance of x1 and x2, which gives you this value, which is a positive value, which means that we have they are correlated in a positive way, which means one increases, the other one increases, which can obviously seen from the plot. The matrix, the covariant matrix, is this one because we have two dimensions, 2 by 2. Element 1, 1 and element 2, 2 correspond to the variance of x1 and x2, and it's also a symmetric matrix and around the diagonal. That's why we have, because covariance of x1, x2 is equal to covariance x2, x1. Okay, so this is just a very quick review about the variance and the covariance, just to give you a very simple intuition what the meaning of each one. Now, PCA and steps. How do we do the PCA? So the first thing, we subtract the mean for individual dimensions, as we saw for x1 and x2. The mean is not equal to 0, so you want to subtract the mean for each sample for each individual dimension, then calculate the covariance matrix, then find the eigenvalues and the eigenvectors of the covariant matrix, and the last step is the actual transformation using some of the components, some of the eigenvectors of this covariance matrix. We will see this in steps, and I think the idea is going to be clear with example. So let's look at the example we had before. We had x1 and x2, 2 dimensions, and even though it's 2 dimensions, but it seems like they look like a 1 dimension in a 2D plot. So the first step, subtract the mean for individual dimensions. We find the value of x1 bar, which is the mean, and the same thing for x2. Then we subtract the mean for each one individually to get this plot. So we still see the same kind of variation, it's just a shifted version. Next step, calculate the covariance matrix. The covariance matrix for this shifted version is the same for the original data, because the only operation we did is just to shift by the variant. By any shift, a linear shift is not gonna impact the spread of the data. So obviously we're gonna get the same value. Now once we do this, we want to find the eigenvalues and the eigenvectors for this covariance matrix. Using any simple tool like MATLAB or anything like that, you can find the values, and we have 2 eigenvectors. This is the first eigenvector, second eigenvector. For each one we have a corresponding value. If you notice over here, the value is really low and the value is really high. And this is what we need to get some insights about those eigenvectors. So let's draw the eigenvectors in the same plot using the same scale for x1 and x2, and plot the vectors. The red one is the one over here, which has the very high eigenvalue. The green one is the other one with a small eigenvalue. So what is the interpretation of this? This means that along the vector with the very high eigenvalue, we have the biggest variation in the data. So the spread, or the very highly correlated, or let's say the big variation in the data, is coming along the vector, the eigenvector with the higher value. And the other value, the small value, does not have as much variation. Now, after we do this, we want to select selection of components and transformation. So this is the main idea for PCA. We will do a transformation in which we multiply the matrix from the left side. So we have our data, the shifted version. We're going to use the transpose, which means each dimension data will be 1 row. So we'll take the transpose of this, and from the left side multiply by the eigenvectors, in which each eigenvector is actually a row. So each eigenvector is a row, and each dimension data is a row. Then we multiply. When we do this multiplication, it is actually a transformation. One point actually I want to mention, that those 2 vectors over here are actually orthogonal. That's why we say orthogonal transformation. And we're multiplying by left. What's going to happen in this case is just a rotation. So selection of components and transformation, we chose both eigenvectors, and we do this transformation by multiplying our shifted data from the left side with the eigenvector matrix. We get a rotated data, which means just a simple rotation, in which you can think of this as a new coordinate system, in which the x-axis is the principal component, which is the eigenvector with the higher value, and the y-axis is the second eigenvector with the lower eigenvalue. So this is just a simple rotation, no loss of information. When you do rotation, you can rotate back by multiplication with the inverse, so you can actually go back to the same matrix. We can get the original data, and the dimensions of this is the same. So we have variation in the y-axis, or let's say this y-axis, the x-axis, we have variations in both of those dimensions, and we can get the original data back. It's just a new representation. What is really unique about this, once you do this process and you find the data, you can actually measure, or let's say find the covariance, and you will see a diagonal matrix. When we see a diagonal matrix for a covariance matrix, this means that the two dimensions are not correlated, which is a cool feature that has applications in some other areas. But for now, we just want to keep in mind that we have the same number of dimensions, and both of those dimensions are uncorrelated. And the main idea that we don't have any loss of information. And this is because we used all the eigenvectors in the transformation process. Next, what we're going to do, we're going to only select the eigenvector with the highest eigenvalue. Highest eigenvalue correspond, if we look back at the data over here, the eigenvector, the red one, is the one that we're going to use, and it has the highest eigenvalue, and it's pointing towards the direction for the maximum variation in the data. And this is why we're interested in this one. Once we do this, so we chose, instead of multiplication by both eigenvectors, we're going to just use one component. So this is why it's called principal component analysis, because we're only using the principal component, and we're doing this kind of transformation for the same data, the shifted original data, and we will get something like this. So the first thing to notice is that we only have one dimension. This representation in 2D is just to make things look better, but only we have one dimension. So all the value, it's just one line. The other thing, now we have loss of information, and we only maintained the variation along the direction of the principal component. We had very minor variation across the orthogonal direction, but that information is lost now. So now we're just maintaining the variation in that direction, in the direction of the principal component. If you want to get back the original data from this, it's impossible, because once you lose this information, you can't go back. What we saw before, we maintained the variation in both directions. Now it's gone. It's just one direction. So again, we lost all the variation across the information across the perpendicular components. However, if we assume that all the information we're interested in is the one along the principal component, this is a good thing, because actually we're reducing the dimension, so we're saving space. We can have more visualization. So now let's think about this process. So again, let's first summarize what we have done so far. We have the original data, x1, x2. Assume you have some data with two features. Let's say x1, the age and hair length, x1, x2, and you're trying to classify based on that information. You get something like this. You have variation in one direction and a small one along the other direction. What we did is to find the shifted version, subtract the mean from x1 and x2, then find the covariance matrix, find the eigenvectors, eigenvalues. One eigenvector along the main variation direction, and the other one is perpendicular. Then what we did next is to transform this data using the principal component. Just a simple matrix multiplication from the left side to get this one-dimensional data. We lost significant information in terms of the variation in the perpendicular direction. So now the question, what can go wrong? Why isn't this good for dimensionality reduction? The idea here is that sometimes, let's assume we have two features, but in the process of measurement, we get some kind of error, and the error is actually significant in one direction. So sometimes you might do this kind of analysis, you get the eigenvectors, eigenvalues, but the data coming, let's say the variation coming along the principal component is because of error. In that case, we're keeping the variation, the information along that specific direction, and we're getting rid of the other direction. So if we're interested in classification, sometimes by this kind of dimensionality reduction, we're losing significant information, and we're keeping information that is not really interesting in terms of the classification process. And the idea is that sometimes you don't know what you you don't really know until you classify. So if you actually start with dimensionality reduction, you might lose some significant information that could have helped you in the classification process. So the only criteria that the PCA depends on is to maintain, is to actually keep the information along the direction with the highest covariance. So this is why we're losing the information if we choose to along the other directions. So this is why you should be very careful when you apply PCA to classification process. It's very easy to maintain the information that is not interesting, and actually to get rid of the information that is really essential for the classification process. I hope this example and the brief explanation about PCA helped you understand the intuition behind the process and why sometimes there is some risk involved in this kind of dimensionality reduction. Thank you for watching this.